Good day to our lecturer and fellow classmates. My name is Sarah Indah binti Sharif, AA250320 from Group 9, Section 4. Today I will present the introduction and meeting discussion for our problem-based learning, project title Infrastructure, Forecasting and Thermal Safety Modeling. This project focuses on applying first-order ordinary differential equation. For case study 1, which is the Green Horizon Smart City, we applied the urban growth model. Our group was given an initial population of 28,000 people in 2026 and 35,000 people after 5 years. Our goal is to forecast the population for the year 2040. This study is data-driven because population growth directly impacts daily water demand. Accurate forecasting is critical to ensure that the ministry proposed water treatment plan is sufficient for the city's future needs. For case study 2, which is the Jambatan Putra Perdana project, we focus on thermal safety modeling. Our group data includes an initial concrete temperature of 95 degrees Celsius and an ambient temperature of 31 degrees Celsius. As site engineer, we must prevent thermal shock, removing from work while the internal temperature is above 35 degrees Celsius can lead to structural cracks. Therefore, our objective is to determine the precise clock time for safe removal. To ensure a well-structured result, we had 2 meetings. On 5 May 2026 physical, we focused on project instruction and assigned specific tasks to each of the 4 members. Next, 7 May 2026 online, we verify our manual calculation against the dynamic access simulation to ensure zero errors. Through this project, we demonstrate how mathematical tools like separation of variables help engineers make data-backed decisions for urban planning and structure safety. This is all from me. Thank you.
Hi everyone, my name is Nur Azila binti Yunan. My metric number is AA250578. Today I will explain the methodology used in our analysis. First, we start with the given differential equation for the both model. dP per dt equal to Kp, and for the cooling model we use dT per dt equal to negative K T minus Ts. Next, we apply the separation of variable method by arranging the equation into integrable form. After that, we integrate both sides to obtain the logarithmic equation and simplify them to get the general solution is P bracket T equal to P0 exponent power KT and T bracket T equal to Ts plus bracket T0 minus Ts exponent power negative KT. Then we substitute the given data for group 9 to determine the constant K. Once the value K is obtained, we use that equation to make prediction. For case A, we calculate the population at T equal to 14, which is represent this year 2040. For case B, we determine that the time required for the temperature to reach 35 darjah Celsius. Next, we calculate the water demand using the predict population. After that, we convert the calculate time into actual clock time starting from 8 AM. Finally, the verify all result using Excel by applying the exp and ln functions and compare them with manual calculation. That's all for the methodology. Thank you.
A very good evening to Madam Nurhana. My name is Luhan Laki Kumar. Now I'll be talking about the manual calculation and Excel file. So, for our group 9, we got this is our data. Case A, PO 28,000, case A, P5 35,000, while for case B, TO is 95 degrees Celsius, and while case B, TS is 31 degrees Celsius. So these are the questions for case 1, as you can see here. We have to use the growth law dP or dt equals to Kp to derive the prediction formula Pt equals to Po E Kt. So this is how we solve it to get the answer. Now we move on to question 2. This is how we solve this question to find constant K. So our answer was 0.04462 per year. Moving on to question 3. We have to find the population growth in year 2040. So we use the base year 2026 to calculate the year in 2040, which is 14 years. So we just use this formula, substitute it, and we'll get 52,294 people. Now you have to calculate the amount, the total daily water demand in megaliters per day. So we know that 150 liters per person per day, and we got 52,294 people. The answer we get is 7,844,100 liter per day. We know that 1 megaliter equals to 1 million liter. So we just divide it, we get 7.04 megaliter per day. So this is the answer for case A. Moving on case B. These are the questions for case B. Case 2. You have to use the cooling Newton's law of cooling, dt equals to K minus negative K T minus Ts to derive the temperature function, this. Okay, and we did that. We did all this and we got this answer. Now we have to find the constant K. Using the question, we see that exactly 2 hours later, T2 equals to exactly 10 degrees Celsius drop. Okay, we got all of the information. We used the Newton's cooling formula, and K we got 0.0849495 per hour. Moving on to question 3, we have to find the precise hour when the concrete hits 35 degrees Celsius. So we used the Newton's cooling formula. We substitute all the values that we got, and T we got 32.64 hours. Now we have to find the precise time. So we know that 32.64 hours equals to 32 hours and 0.64. Then we have to times it with 60 minutes to find the exact minute, which is 38 minutes. And we know that T equals to 32 hours and 38 minutes. For question 4, we have to find the exact time for the crew to begin their formwork removal. Now we know the post start at 8 AM, and we got the answer 32 hours and 38 minutes. 32 hours is 1 day plus 8 hours. So the time starts at 8 AM plus 1 day, which is the 8 AM next day, and 8 AM plus another 8 hours, we got 4 PM the next day. So 4 PM plus another 38 minutes, we got 4:38 PM the next day. So the safety removal time is 4:38 PM the next day. So these are the answer for our case B. I'll move on to the Excel file. Okay, now I'll continue for the Excel file. So for case A, the initial population was 28,000, while the population after 5 years is 35,000 in the year 2035. So to calculate the constant K, I use this formula, as you can see here. While for population 2040, I use this formula. And to find water demand, I use this formula. So this is the data that we used to find the graph. So we got the year. We just know it's until 2040, and this is the T years, and this is the formula I used to calculate the population. I use this formula, and this is the graph for the using according to the data. As you can see, year and population. Now in the question, we also had the dynamic forecast. So the target year was 2050, and the years from 2026, I use this formula, which is 34 years. And forecasted population that time 2050, I use this formula to calculate it. And water demand on that year, which is 2050, I use this formula to calculate it. So I'll move on to case B. Okay, for case B, the initial temperature was, as we know, 95 degrees, ambient temperature Ts 35 degree, and temperature drop after 2 years, which is 10 degrees. Now to calculate temperature at T equals to 2 hours, I use this formula. Basically, just can minus it ourselves. To find the cooling constant K, I use this formula. To calculate time is 35 degrees Celsius, I use this formula. To calculate time, I use this formula. And to calculate safety removal prop time, I use this formula. Now we move on to the data. We have time, clock time, temperature and safe status. These are the time we use until 34.5 hours. Time. This is the formula. To calculate clock time, this is the formula. To calculate temperature, we use this formula. And to calculate safe status, I use this formula. And this is the graph according to this data. So you can see time against temperature against time. And as you can see the safety status, I use red color for unsafe and blue color for safe to differentiate the good and the bad. And as you can see for temperature, there's a green thing. The green color represents the temperature that's below 35 degrees Celsius. So that's all from me. Thank you.
First, let's talk about verification. As engineer, we cannot rely on a single source of data. We compare our manual derivation using the separation of variable against our dynamic Excel model. I am pleased to report that for Group 9, our result matched perfectly. This consistency gives us the confidence that our constant K equals to 0.0446 for growth and K equals to 0.0864 for cooling are mathematically sound. In case study A, we projected a population of 52,246 by 2040, while the map gives us a water demand of 7.84 megaliter per day. We must look at this critically. As a consultant, I would recommend building a plan for exactly 7.84 megaliter per day. We need to account for peak hour and system maintenance. Therefore, our proposal is to set the infrastructure capacity at minimum of 8.0 megaliter per day to ensure the city's long-term sustainability. In case study B, the discussion shifts to safety and structural integrity. The 95 Celsius initial temperature is extreme. If we were to give in to project management pressure and remove the formwork early, the concrete would suffer from thermal shock. This leads to micro cracks that compromise the bridge lifespan. Our analysis shows that physics require a cooling period of over 32 hours. There are no shortcuts when it comes to public safety. To conclude our presentation, here is our final engineering advice based on ODE models. For the Green Horizon Smart City, we recommend the immediate planning of a water treatment plant with at least 8.0 megaliter per day capacity to support the 2040 population surge. For the Jambatan Putra Perdana Paya, the safe window for formwork removal is exactly 32 hours and 5 minutes post-pour. Operational schedule: since the pour starts at 8 AM on day 1, the site supervisor must wait until 4 or 5 PM on day 2 before authorizing the removal. Ultimately, this project proved that first order ODEs are powerful tools. They allow us to transform raw data into life-saving decisions and sustainable urban planning.